Welcome back. So we're basically now quickly looking at Lab 8. So we're using for this the codes that Marcel Ramos and Pino have used in the spring semester. And I would like to explicitly thank them both to put this at our disposition. So we can now quickly look at the Lab 8 Challenger O-ring. So this is the example that Professor Sang has posted. I remember this as a little anecdote. I still remember this example because he also had it when I did BIOS 1, so the applied BIOS 1. So in 1986, there was a catastrophic launch of the Challenger space shuttle. And so I remember seeing the explosion as a kid. So that was a very sad event. And the reason for that was apparently that there was an O-ring that kind of got damaged and heat was basically getting into the fuel tank. I'm not an expert on aviation and space aviation, but it seems like temperature had to do with the damage of this O-ring. And that's the example that essentially Professor Sang has put forward here. So we have here this plot that depicts damage as a function of the temperature at launch. And we can use this data. This data is posted in the lab data as pre-challenger.xls. I want you to load this data into R. You can convert it in a CSV file. This can easily be done by just clicking on Save As and changing the file format to what I would recommend, MS-DOS, comma separated value file, CSV. This will allow you to save it as a CSV file. And then you can load it easily into R. There are some Excel packages that allow you to load Excel packages. It's probably easier you load it as a CSV file. But let's quickly look at the codes that Marcel and Pino have put forward. So I hope you all can see my screen well. And I'm trying to enlarge the whole screen a bit. So we're basically having here on the first line, we have the remove list equals ls. I have elaborated on that, I believe. So the list that is being removed is all that is ls, which is in the environment. So ls alone gives you all the object in the environment, which you see here on the right. rm list ls removes everything. You're setting the working directory. And again, I'm repeating how to do that. You basically go on the folder that you want to make the respective working directory, you right click on it and you click option on a Mac. You can do a right click in Windows, you go on properties. On a Mac, it's easier. Once you press the option, you can copy lab as path name. You can just bring it into R. So you control V now, it basically gives you the folder structure and the directory. In Windows, pay attention, please, because you need to change these guys for these guys. So Windows is traditionally working with something that's called backslash. So that is a slash in the other direction. This is a slash. So you need to replace the backslashes into a C recognizable format, C++ recognizable format, which essentially is the slash rather than the backslash. So this is the setting the working directory. Marcel is doing that, which is not a bad idea. You can also use a different way that I have shown in earlier classes. The foreign library, as we know, allows for us to read SPSS files. We can now, with the table function, we're doing exactly what Professor Sang did in the lecture file. Essentially, with help.rct table, we can basically create with the help.rct file a table. We are essentially running here now the very same fit file. So if we do summary fit, we're seeing this fit file that we have discussed in class. So we have, with being treated, we have a higher probability of odds for risk. So exponentiating that will allow for us to get the odds ratio for being link status, of being linked to the primary care physician when being treated. So now we have the Titanic data. So the Titanic data, so R is full of these data sets, and these are really super useful. So this is really a fantastic kind of possibility to test various models, test packages. And if you load library Titanic, and you may have to install it, you can actually load Titanic train into your environment. If you look at it, essentially you will see the passenger names, you will see passenger ID, survived yes, no, the class of that individual was traveling in, you have sex, age, siblings, ticket numbers, fares, how much they paid for their fare, embarked on the cabin class, and the cabin, what the cabin was essentially, in which cabin they actually were. We don't need to set the working directory anymore. We can load also now from the working directory, we can load the Titanic train RDA file, which essentially is just giving us the same. We can also download it online. So now we want to look into sex. So we have 314 females and 577 males. So we had 891 passengers. If we are now creating a table, a 2x2 table of train and survivor, so Titanic train survived, whether the passenger survived or not, and we basically see females versus males. We see that there's some form of a relationship between survival and gender. Seems like more females in percentage terms seems to have survived, which is leaves room for interpretation. I'm not sure what the interpretation is, but it may have to do with staffing. I'm not sure this includes passengers, but I'm not sure I know enough about Titanic to really give a statement there. Likely there was more male staff. That's one way I could go in my thinking. And staff likely would not fit on the lifeboats, and maybe something along these lines. I don't know. Not an expert. Not sure what the interpretation would be. Okay, so we have fit GLM survived as a function of sex. Family is binomial, just like we've seen it up there. Data is the Titanic. And we see now the summary fit. We see our suspicion confirmed, significantly confirmed. We see here the intercept, which is the overall probability of, so the overall odds ratio of survival. And we have here the sex male, which essentially is when you were male, you had okay, so I need to take a step back and do some calculations. So something threw me off. What threw me off is basically it's coded as survived as a 1, whereas death would be 0. And what I said before, so in my world, we usually code died as a 1 and survived as a 0. So now speaking about this on the camera, I kind of got a little bit tripped over my own way of thinking. And so obviously, so this is survived. And the survival probability is significantly lower in males, which is seen here in the risk ratio, where we basically have, so we have a probability of survival. It's still throwing me off. Okay, we have so a 74% survival probability in females, whereas we have an 18% probability of survival in males. That renders a survival risk ratio of 0.25 for males, meaning they were more likely to die and less likely. It's a 75%. It was 0.2, and so they had a fourth of the risk to survive as compared to women. It's still throwing me off. I still would have coded it differently, but it doesn't matter. It's like, okay, let's run with it. Okay, so this is how you need to interpret it. This is how it was shown for males in the logistic regression. You essentially get 0.18, 0.74 divided by 0.18 is now a fourfold greater probability to survive when you're female. So this is the other way around. We just changed the way to look at it. The reason why odds ratio and risk ratio are differing from each other is the same as in epidemiology. It has to do with the number of events, rare diseases, risk ratio and odds ratio are closer to each other. Whereas in less frequent events, they're a little further apart. Good. But this is essentially the way how you look at it. So we have now our summary of what is happening. Sorry for that. So summary fit shows us the logistic regression, shows us the survival probability for males. So the odds ratio, all else being equal, and you can adjust for additional parameter. You can, for example, you can also include a different parameter. LS Titanic train. You can look into fair. So X and fair will now show us a multivariable regression where basically there's not much of a change to the gender distribution. So even if you adjust for fair, you still get a significant signal from gender. Good. Take the fair out. And we're saving this, and this is going to be the one I'm giving you. So now if we look now at the addition class, so this is basically library GLM2. You can install this, and the code is right there. Data is CRABS. So CRABS Y satellite. I don't know what the example is, but essentially you can use it just in the way that Bino has done it here. We can look like this. Data sets. Help. Crabs. Horseshoe crab data. It gives 4 variables for each of 173 female horseshoe crabs, provided random samples of the data with replacement. So we're basically getting derived from data. go with random samples. So, okay, dark equals yes corresponds to good spine. Yes corresponds to S smaller than 3. Okay. This is the example. So we have satellites as a number of male partners in addition to the female's primary partner. And as a satellite as a function of width. So female horseshoe crabs, we're testing the research question with female horseshoe crabs was a wider, was greater width, essentially get more male partners in addition to the primary partner. Okay. So this logistic regression is testing the promiscuity of horseshoe crabs. And we're having a fit GLM Y satellite. It's always an interesting variable name for this topic, but okay. Okay, so summary fit will show us now whether the width is significantly associated with the number of male partners in addition to the primary partner. And it essentially is. We can now extract them and load them into a package. So we have now -12, which is our intercept. We have B1, which is our 0.4972. We exponentiating that, we're getting to a really small intercept. We're getting 1.64. So there's a 1.64 higher odds to essentially get additional partners. With a width okay. This numeric is greater than 0. Crabs, Y satellite. Okay, they have a max of 1. So that means that they have more than one primary partner, number of male partners, satellite, Y satellite. Okay, sorry, I should have probably prepared it before. Because satellites is more than one, so it's more than one partner. So they have more than one partner. Then Y satellite is a 1. Crab satellite. Okay, so that's one of the standard. Okay, so Y satellite is more than one partner. X is crab's width. So we're now calculating this in a more classical way. So we're basically plotting this. So we're having now the to the x-axis, so that's the width as a function of the probability. So we are seeing now we're seeing here now the probability of x as a function of the width, which is a sigmoidal function. It's not strictly linear. So we're seeing now x.1. So this is now the calculation, and I alluded to that earlier when I talked about that you can use this to calculate the odds ratios, right? So when you are wanting to calculate an example for one individual, you have the xi, which is 26.3. You can basically set this to 26.3 and you calculate the probability with 0 for a female with a width of 26.3. You can basically calculate this here as 0.67. When you use this as an appline, you actually see here that this should be here at 0.67. So this is actually very nicely done and very nice to illustrate how useful that actually can be. And if you exponentiate this now, you essentially get a width of 1.64. So if you have a width of, I don't know, why is this actually? Oh, that's the estimated odd. Okay, so B1 is our width. The odds ratio that is shown is the increase in the odds ratio for a 1 centimeter increase in the width. So there's an increase of 64% with an increase of 1 centimeter from the average. So meaning the average would essentially be here the intercept, right? So you have an intercept of 0.67 and the intercept of width, everything that exceeds that, this is our intercept. Everything that exceeds that is basically increasing the odds ratios. Good. So this is the example of the crabs. So we have now Titanic and the crabs. And I think this kind of sufficiently illustrates. Please go through those examples. Post questions to the discussion board if you have questions. And try to be again more responsive. So I'm back now in New York. I will be more responsive. So I apologize if I wasn't sufficiently responsive during my travels. But I'm now back and homebound and New York based. Can make myself now more available. Also in case there are interest in additional explanations. We are now also looking at our Challenger ring example. The question here is that we want to understand what's the probability of a damage is on the day when Challenger is launched, conditioning on the temperature. So we have a binary outcome, which is damage, no damage, and we want to understand to what extent this associates with the temperature. So what I want you to do, I would like to have as an outcome, and I would like for you to investigate this data and also plot this as a function of the temperature. So show me that probability curve. I would like to see this probability curve in order to make sure that you really are on board with the concept and have really followed along. It's not going to be that difficult because you have the code right there. Okay, so I will post this. I will be observing the discussion board. Please let me know if there are any questions, and good luck with the lab. And see you next week, or see you on additional check-ins if you're interested. Okay, good. Have a nice evening. Talk soon.